All right, so we are talking about grammars for constructing languages. And at the very end last time we were discussing how any regular language can be converted into a grammar. Any NFA, I'll just refresh our memory here. Any NFA can be converted to a grammar. And it's very easy to do, provided, you just have to remember this strategy. But here's an example of, this is sort of an old even versus odd style DFA. This one accepts any string with an odd number of A's. But if I were to convert this to a grammar, remember the way to do it is you give names to the states. I'll call them S and T. Those are called non-terminal letters in the grammar. So I have S goes to some stuff, and I'm going to have T goes to some stuff in my grammar. S is the starting grammar symbol because S is the starting state. And then the grammar, remember these are called productions in the grammar, are based on the transitions from the NFA or DFA. And for instance, this arrow S goes to T with an A means in the grammar S goes to AT. And there's also an arrow S goes back to S with a B, which makes the grammar production S goes to BS. And then for the T, I have an arrow T goes over to S with an A, so that makes T goes to AS. And I also have T staying where it is with a B, which means T goes to BT. And T is an accepting state, which means I put or epsilon on that one, because that means the grammar derivation can actually finish if we're in a state T. All right, so it's a very simple, direct sort of translation of the NFA into a grammar. Going the other way around is harder and generally speaking is not even possible. That's because we already know some grammars can make non-regular languages. And so if you have a grammar of a non-regular language, then certainly you could never convert that into an NFA because that's what non-regular means. You can't have it. You can't make it with the NFA. But I will say, something I want to talk about just for a few minutes, some grammars can actually be converted back into a regular, into a NFA. Some grammars can be converted to NFA. And I'm talking about, like, specifically if your grammar happens to look kind of like this one here. The important property of this grammar is that every production has some, like, a little letter to the left of a big letter. If that's always true and there's no other stuff around it, then you can always convert that kind of a thing back into NFA. For example, what if I have this grammar? S goes to AS or BT, T goes to AS or BT or S or epsilon. This one has the same general structure, so each production looks like something like X goes to AY, right? Something like that, where it's just the non-terminal goes to a little letter followed immediately by a big letter, all right? If they all look like that, or perhaps there's an epsilon in there also, which indicates accepting states. If they all look like that, then you can just directly translate this back into an NFA. So the NFA has, S and T are the states, right? And then we can just do the process in reverse. You translate each grammar production into an arrow. So when I see S goes to AS, that's an A loop on S. When I see S goes to BT, that's an arrow from S to T with a B. Then I have T goes to AS, which is an arrow from T back to S with an A. T goes to BT is a loop on T with a B. T goes to S. Anybody want to, how can we express that? T goes to S. Yeah?
Epsilon from T to S.
Yeah, how about T going back to S using an epsilon, right? When I see S here, of course, that I can interpret as just epsilon S because epsilon is like nothing, right? So maybe I'll just put A comma epsilon here. So that epsilon there represents the t goes to s arrow. And then finally I have t goes to empty string, and the interpretation of that is there's an accepting state, or t is an accepting state. All right? So you can convert the other way around if you're lucky. I mean, the grammar has to look, it has to be in this very specific format in order for this to work at all. All right? We can get slightly fancier as far as the format goes. Slightly fancier. Here's one where instead of single letters, I'm going to put longer strings perhaps. Like, you'll see what I mean. S goes to ABAS or AT, and T goes to AAT or S or epsilon. So this one is, mostly the same, but it's a problem. This, for instance, S goes to ABAS. It's not clear what exactly to do with that, but don't worry about it. S goes to ABAS. You would be tempted to just do this, ABA, but of course that's not allowed. That's not allowed for an NFA. Every arrow of an NFA has to have just a single letter on it. So there's no such thing in an NFA as this. But really what you want is you want to be able to start at S, do A, then B, then A, and then end up back in S. And the sort of cute way to do that is I'm just going to invent a few new little guys here with an A, B, A, like that. So when you see in your grammar some strings longer than a single letter, you need to create extra states in order to accommodate those extra letters. But otherwise, there's no other funny business that can happen here. So this one allows you to start an S and go A, B, A, and back to S. All right. Then I also have S goes to AT, so that's just an ordinary single arrow. I also have T goes to AAT, and here I'm going to do that same little trick. So I go A like this, and then also A back like that. So that's T goes to AAT. And then also T goes to S, so again, that's going to be an epsilon arrow from T back to S. And then T goes to epsilon indicates that T is an accepting state. All right, so this is how you handle a grammar with some kind of extra letters on the left side. It still only works if the letters are on the left side. If there were also letters on the right side of this S, for instance, then you'd be totally screwed. The same approach doesn't work at all in that case. You would have to use completely different methods, or maybe it would be entirely impossible. All right, I got one for you all to try. This is not really hard if you know what's going on. How about this one here? You make this into an NFA. S goes to ABS or BT. T goes to BBAS or AR. R goes to just BS or ABT or Lil B. You have to think about that one on your own. What to do with this Lil B. Instead of, if it were an epsilon, you just make that into an accepting state. Instead I said Lil B. See what you think about that. Think about it a little. I'll give you a few minutes. Maybe I'll walk around and see how you're doing.
Thank you.
You okay so far here?
Yeah.
this B is something like that. I can actually say how to do it, but I encourage you to think it over. Yeah. Okay. Think about the little B. It's not. Oh yeah, not any of these.
Yeah.
Yeah, that's good. No. I mean, so this arrow is correct. Yeah, but it doesn't mean S is an acceptance. Okay. Mm-hmm. Yes, what to do with the little leaves. Okay. Yeah, looks good. This, because this means R
It's going
goes
back
to
to
the R,
okay.
which is not this. Yeah. This has something to do with acceptance states.
Okay.
Because this grammar, this then we can finish.
Okay, so would it just be this? Okay.
Doing all right? Yeah. Thinking about little b? Yeah, it has something to do with acceptance states. So that. All right, can we chat about it? I see a lot of people worked it out. So I think it's fairly straightforward, although you have to think a little bit about what that little b is supposed to do. But other than that, there's not a lot of surprises here. I'll just put my str like this. So S goes to ABS is like this. S goes to BT is like that. T goes to BBAS. So there's B, B, A, back to S, something like that. T goes to AR is just this. R goes to BS is that. R goes to ABT, like that. And then finally, the extra B. So this has something to do with accepting states. If that B were an epsilon, it would just mean that R is an accepting state. As I was going around, I would say what this means to me is if you're in R and you would do a B, then you can be accepted. And so this is how I would do that. If you're in the state R and you do a B, then in terms of the grammar, that means the grammar derivation can end at that point. In terms of the diagram, sorry, I gotta scroll it up. It should be like that. All right, any thoughts about that? Once you know what you're doing, there's nothing really very difficult about that. There's a name for this form of grammar. We're not gonna talk a whole lot about this, but this format here is called a right linear grammar. It means that each production, what that means is each production is something that looks like X goes to SY, where this one is all terminals, or X goes to S, which indicates that's like the extra little b here. In that case, it's called right linear. The word right because all of the non-terminals are on the right side of the terminals, all right? If it's the other way around, if the non-terminal appears first and then the terminals, then that's called a left linear grammar. But there are the same tricks don't work for left linear as right linear. All right, so, and there's actually a lot of like classifications of different types of grammars, and these right linear grammars are very simple ones, very easy to work with because they can always be converted into NFAs. And there are other types of grammars that we're going to be discussing. This is kind of one of the very simple types of grammars. Automatically, the language is regular if you're using a grammar of this type because you can always convert to NFA, so that makes it regular. All right, what I would like to talk about, probably for the rest of today, is a more interesting class of grammars. I would like to talk about what they call the context-free grammars. This is another type of grammar. I'm going to write this as CFG, context-free grammar. This is another type of grammar which is not so simple as the linear ones because those are very simple. It's a little bit, well, it's quite a bit more, allows quite a bit more things. But anyway, I will just say what it means. G is a context-free grammar when each production looks like X goes to, I'll just put a little s here, where this is a single non-terminal. I hope everyone knows what I mean by non-terminal. Remember, means like the capital letters, the letters in the grammar which can become other stuff. And then terminal is like the little a and the little b. Those are letters which do not become anything else. So a context-free grammar means every production looks like a single non-terminal on the left side of the arrow, and then on the right side of the arrow, any string of terminal and non-terminal. So you can have anything you want on the right side of the arrow. You must, on the left side of the arrow, have just one single non-terminal symbol. All right? And basically, every example we've ever talked about is already like this. You have just one non-terminal on the left side of the arrow, and then it can become several other things. So, for example, i.e., I should say e.g., for example, you know, S goes to AS or BT or epsilon, T goes to BT or ABS or ASB or BAB, something like that. I'm just making this up. This is a context-free grammar. All that means is the left side of every arrow is just one single non-terminal. So this is context-free grammar. That's because the left-hand side of each arrow is a single non-terminal. That's what context-free grammar means. All right? A non-context-free grammar is very weird. It has some grammar arrows where the thing on the left of the arrow is not just a single non-terminal. So, for instance, if I had something like S goes to AT or TT, T goes to epsilon or BS, AT goes to BBB. This one is not context-free, and it's because of that last line where I have some weird, funny business on the left side of the arrow. That makes it not context-free. So this is not context-free grammar because of, well, this funny business on the left side is not allowed in a context-free. So if you see weird stuff on the left, that is not context-free. All right? The term context-free is a little strange. What it is meant to indicate, so why is this called context-free? Context-free. For example, a rule like this, T becomes BR, that rule is context-free because there's no funny business on the left. So this is context-free because it means T can become BR, sort of wherever you see it, right? That's what that rule means. Whenever you see a T, you can change it into a BR, all right? Whereas something like, that last line or something like this, AT goes to BR, this would be not context-free. This line is not context-free. Because what this means is, it means T can change, but only when next to A, right? This is your interpretation of that rule. You are allowed to do a substitution involving that T, but only if there's an A next to it. And that is to say, another way of saying this is only when next to an A. Another way to say that is only in a certain context. That's why the word context-free is used here, all right? So in a rule like this is a substitution rule, but it requires a certain context in order for you to use that arrow, right? The T has to be next to an A. Whereas this one up here is called context-free because it just means the T, whenever you want, can turn into this. And there is no context necessary. I'm just trying to explain the terminology here. We don't really have to think too much about that. It's just called a context-free language, or a context-free grammar, all right? This gives us a new category of languages. Oops. Any language generated by a context-free grammar is called a context-free language. And we're going to write CFL, a context-free language. All right? So this is another kind of category of languages. So far in the course, we've only really had one category, that is regular, and then not regular. But here's another one. There's the context-free languages. These are the ones which can be generated by context-free grammars. All right? Now, I will point out, let's just talk briefly about what do context-free languages have to do with regular languages? Is every regular also a context-free, or is every context-free also regular? That's the kind of thing that I want to think about. As far as regular languages and their grammars go, remember any regular language has a grammar. We talked about at the when we started today. If you take a regular language that is from an NFA, you can convert it into a grammar. And actually, those grammars have this right linear format to them, right? Any regular language has a right linear grammar, right? Those are ones that look like, something like S goes to AT or BS, T goes to BS or epsilon, right? Those are the ones, if you got them from an NFA, then your grammar is going to look something like that. And this is automatically context-free because the left side of the arrow has no funny business there, all right? So any regular language gives you a grammar like that, and these are always context-free. These are always context-free grammars. So that means any regular language, maybe I'll write this like a theorem. We don't have to do the proof of this or anything, but it's an important thing that everybody should know. Tell your friends. We can tell them at board game night if they don't know by then. Any regular language is context-free. Right? Because when you make the grammar out of it, actually the grammar ends up being one of these linear types, and those are always context-free. No funny business on the left side of the arrows. All right? Any regular language is context-free. What about the other way around? Can you make, so the question is any context-free language regular? Or is it possible to make a non-regular language out of a context-free grammar? Anybody, I don't know if you remember, but we actually did talk about last time an example of a grammar that can make a non-regular language. So recall, NIMB, S goes to A, S, B, or epsilon. The language here. What's the language of that? This one, you can do the first step over and over again to create A's and B's, and then you finish by making epsilon at some point. Yeah.
A to the n, B to the n?
Yeah, the language for this is A to the n, B to the n. Right? If you do this first arrow once, then you can make AB. But if you do it twice, since the S is in the middle every time, it becomes AABB. If you do it 3 times, you get A cubed, B cubed, and so on. So this language is A to the n, B to the n, which of course everybody knows is not regular. But it is a context-free language, all right? Because it comes from that grammar, and that grammar is a context-free grammar. So it means the theorem that I wrote up there, you cannot say the same thing the other way around. Any regular language is context-free, but not every context-free is regular. So not all context-free languages are regular. Right? Not all context-free languages are regular. What it means, and this is going to be a major theme for the rest of the semester, there's kind of like a, if you consider like the universe of all languages, you can sort of classify them into languages of increasing complexity. And what we have so far, this is kind of like a very simple Venn diagram, but you have sort of the universe of regular languages. Those are the simplest kind of languages that we are talking about in this course, but they live inside of a larger universe of context-free languages. All right, and an example of a context-free which is not regular, I'll represent with like a little dot over here. A to the n, B to the n. Right. This is one example of something which is in the larger set of languages, but not in the smaller. So that A to the n, B to the n is part of this larger universe of languages, but it's not regular. All right. And this way of looking at all languages has been very influential in the development of the subject. So I don't know if it surprises you, but at this point, since I draw this diagram, you may wonder, is there more stuff out here? And the answer is yes, there are things which are not context-free. And in fact, as we get closer to the end of the semester, actually we're going to be drawing, 2 or 3 more layers around this of increasingly complex types of languages. So that's kind of a very broad picture of where we're going with this. One of the ones farthest out are the languages which can be generated by any Turing machine. Remember, that was what I said on day 1 this class was going to be all about, and then I never said those words again. But the Turing machine is one of the more complicated types of machines for generating complicated types of languages. All right, there's actually a name for this whole diagram here. This is called the Chomsky hierarchy, because this is named after this guy Chomsky that I mentioned last time. Chomsky invented grammars, which makes him sort of a legend by any rights. But Chomsky also invented grammars and then also came up with this classification for different types of grammars. I don't think Chomsky was thinking of regular languages in terms of NFAs. I think he was thinking of these as, this is the domain of linear grammars, and then this is the domain of context-free grammars, and then he made some even more complicated categories beyond that. But yeah, this is called the Chomsky hierarchy of grammars, or Chomsky hierarchy of languages. And this is kind of the structure for a lot of the rest of the semester. But before we, move on to grade more and more complex languages, I would like to talk about context-free grammars. Just a standard kind of thing that you want to be able to do is building context-free grammars. This will be a bunch of homework problems you'll see about, I describe to you a language, and then your job is to make a grammar which makes this or that language, right? Make a context-free grammar. Because the non-context-free ones are pretty wild. But building context-free languages. So I give a language, you make a context-free grammar for it. That's the idea here. All right. Now, there are certain types of examples that we've already talked about. So if it's regular, if the language that I'm giving you is a regular language, then you can make an NFA and convert it into a grammar, just like we did at the beginning of class today. So that's an easy case. So if it's a regular language, make an NFA and then convert to a grammar. So in that case, there's not, I mean, this might still take a few minutes, but at least there's no theoretical boundaries to, no obstacles to doing a construction like that. All right. Let's talk about some non-regular languages. Now, I don't know if you've gotten a feel for it after doing all these derivatives examples. The typical thing which seems to make a non-regular language, what makes it non-regular is when you have something like a to the n, b to the n, and it involves the fact that you repeated this n 2 times in different places of the string. All right, that was a basic feature, at least of a lot of the examples that we did on the homework for this week, for instance, of non-regular languages. This kind of a thing, I'm going to refer to this, I'm going to call this balancing. What I mean by balancing is these two ends, these ends have to be the same. As you think of the string as somehow growing, as every time you do one of these grammar steps, the string gets bigger a little bit. But while the string is growing, these ends must stay the same. And that's why I think of this in terms of some kind of balancing, all right? Those two ends must stay the same. Another way to think of this is each A is balanced by a B, right? And the strategy, when you want to make a grammar which has this type of balancing, now that particular example, we already know what the grammar looks like, but the way that you want to think about this, each A is balanced by a B, so our grammar must create the A and the B together in the same production. This is the only way you can be sure that there's going to be a matching amount of A's and B's, is if every time you make an A, you automatically make a B at the same time. All right? Because if you let one step of the grammar make an A, but then the B comes from a different step, then it might get messed up if you do the one step twice or something like that. You have to make them at the same time, all right? And in this case, so specifically to get A to the N, B to the N, now I have to imagine that every A is balanced by a B, and to produce this, you have to actually sort of grow this string from the middle outwards. So to get A to the N, B to the N, you balance A and B, and I will say grow the string from the middle. Why is that? I mean, it's just because if I think about, say, if I wanted to create the string like A to the 5, B to the 5, it would have to look like, you know, A, B, 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 B. But if I want to create A's and B's at the same time, you can't create this just straight up left to right, because you have, if you're going left to right, you have to make a bunch of A's first and then somehow remember how many A's you made and then make the same number of B's. That's not going to work in a grammar. Instead, you grow the string from the middle. That's easy to do. You can just make one A and one B on each side and then do that over and over again from the middle. That's why the grammar for this looks like S goes to A, S, B, right? This is balancing A's and B's and growing the string from the middle. So even if you don't remember this, we just talked about this example a moment ago, but this is actually a fairly easy construction once you have this way of thinking in your mind. Balancing things and growing the string from the middle, all right? So let's try some sort of similar examples, variations on that. How about A to the n, B to the 2n? You have to think about what exactly is being balanced here. In the previous example, A to the n, B to the n, each A is balanced with a B. Can anybody say something, of a similar format, but what precisely is being balanced here? Yeah?
Every A, there's 2 B's.
Yeah, for every A, there's 2 B's. And I think in order to make this work, again, I want to have the string growing from the middle. And I make the A on the left, and 2 B's on the right. So the grammar here should look like S goes to A, S, B, B, or epsilon. The or epsilon is just to do something to finish at the end. Yeah, excellent. All right. How about, I got just 2 more simple examples of this. How about A to the n, B to the n plus 1. This is a different type of variation of the same kind of thing. This one says there's just 1 extra B. So the way I would think about this is the A's and the B's, actually they are still balanced. 1A goes to 1B, or 1A goes with 1B. It's just that somehow there's 1 extra B that you get. If you are thinking of doing this again to make 1 extra B, you're wrong. When you say this, it does look like you get 1 extra B, but remember, you're going to do this step over and over again. So you get an extra B every time, which is not what you want. You want overall just 1 extra B in total. Any idea? Yeah?
Was the epsilon?
Replace the epsilon with a B, she says. I like that.
But not. Yeah, just.
Like that. Yeah, so just 1 B here, so this will make it perfectly balanced, A's and B's. But then at the end, you just add 1 extra B. Great. This makes 1 extra B at the end. You don't want the extra B every time. That's the moral of the story. Okay, how about, here's another slight variation. A to the m, B to the n, where m is greater than n. So this one I would say is kind of like the previous one, but here we have several extra A's, right? Could be 1 extra A, but it could also be, 2 or 3 or whatever. It's just the number of A's is more than the number of B's. For this one, this is, I suppose, a little tricky. I want to do something like this, but instead of B here, I want it to be A to get an extra A. But actually, I don't want just 1 extra A. I want perhaps a whole lot of extra A's, right? So the way my strategy for that is going to be like this. This is a little cute. This part just by itself makes equal amounts of A's and B's. And then I want to, for this OR thing, I want to put over here basically any amount of extra A's. And the way I'll do that is I'll make a new non-terminal like that. Yeah, maybe with that. So the idea here is by doing this first arrow over and over again, we get precisely balanced A's and B's. And then at some point you just decide you're done. And when you're done, you go down to this one, and this one just creates a bunch of extra A's, some number of extra A's. And I put A here rather than epsilon because I don't want this to make 0 extra A's. Yeah?
Does it not work to do A as B and then or lowercase a s and then or epsilon?
This is a good idea. I think in this case that works. He said S goes to ASB or AS or epsilon. Is that what he said?
Yeah.
Yeah, so this means you balance A's and B's. What's weird about this is it allows you to do this step a bunch of times, then do this step a few times, and then go back and do this step some more. You should be a little concerned that maybe your ordering is going to get messed up. Although I think in this case, it doesn't mess anything up. But I would suggest that this is a cleaner way to think about it, and in other examples, this is a more appropriate approach. But I think this is also correct in this case. Yeah. There are, as always, many different ways to write a correct answer for building a grammar. All right. Yes.
If you have epsilon at the end, will m and n be equal to each other?
Here. Oh, yes, you're right. So this epsilon should be. How would you fix that?
Just a.
Yeah, just a little a. Yeah. Yeah, thanks. I think that might be what he said to begin with. Yeah, great. Thank you. All right. So this is how you manage this kind of balancing thing. I have two other little tricks. And with all these sort of tricks together, you should be able to create grammars for whatever thing you might encounter on the homework or such. So we talked about regular languages. You just make an NFA and convert to grammar. If there's some kind of balancing, you do some tricks like that, where you sort of put the S in the middle and do some interesting stuff on the two sides of it. Another simple trick. Whoa. I found my pen gets messed up, but only like late in the day. I have class at 11, and it works perfectly. And then it never works well at the end. I think maybe it's my iPad is overheating. I don't know. Maybe my hand is overheating. It's kind of hot in here. Concatenations. There's a simple trick for building grammar of some kind of a concatenation. What I mean by concatenation always just means like two strings which are just stuck together end to end. So for example, here is something like, this looks very complicated. A to the n, b to the n, x, such that x has an even number of a's. All right. This, when you see something like this, the appropriate thing to do is realize that this is actually a concatenation of two simpler things. This part is balancing, and this part is regular, right? Because this thing, x has an even number of a's, I can make an NFA for that with two states going back and forth, all right? And so this whole language as a whole is a concatenation of two simpler things. And so the strategy is make a grammar for each of those two simpler things and then somehow patch them together into a big mother grammar for the whole thing. So first I'm going to do a grammar for each. The first one is going to be S goes to ASB or epsilon, but I'm going to call this S1 because I'm going to have two different grammars, and this represents the first one. All right, so that's the balanced part. Oh, it ain't pretty. Can you see that? Sorry. That's the balanced part. I'm calling this S1 because that's the first grammar. And then the second grammar I'm going to get by making a little NFA, so you might want to do this sort of on the side here. An even number of A's is like this, and that should be the accepting state, right? This NFA it's a DFA actually, but it will accept any string with an even number of A's. And so the regular part, this needs two states, right? I mean, it has two states, so when I turn it into a grammar, it needs two non-terminals. I'll call them S1 and, call it anything but S1. S2 and T, right? So the one on the left I'll call S2, and the one on the right I'll call T. And so the grammar for that, just by what we did at the beginning today, S2 goes to AT or BS2, and T goes to BT or A. S2, and S2 also gets epsilon because it's accepting. All right. So I have made a grammar for each little piece. Now I just need to patch them together into sort of one big grammar to rule them all. So to concatenate them, and this is just a very simple trick that you just have to remember. You just begin like that. S goes to S1, S2. So if you begin your grammar like this, it means whatever I start with, my string that I'm creating, it must immediately look like something from the first grammar followed immediately by something from the second grammar, which is exactly what we want it to look like in my language up here. All right. So my final answer, this is a little sort of disorganized, but my final answer, I'll just say, our grammar is, I'm going to roll up my sleeves. Maybe this will cool my hand down a little. If the tours walk by, they'll think I'm really into it. I am into it, although I'm not, I don't know if you realize by now. I'm not all that exuberant even when I'm into something. I say I'm into it, and you just have to believe me. So you begin with S goes to S1, S2, and then S1, I'm just copying what we said before. A, S1, B, or epsilon. S2 goes to AT, or B, S2, or epsilon. T goes to BT, or A, S2. There you go. You can impress your friends. This looks crazy. That you actually came up with all of that? Well, yeah. It comes from doing two sort of small and fairly simple examples, and then you patch them together in this way. All right. This is how we handle a concatenation of two languages. Any thoughts about that? I got one more trick, and then we can try some examples to sort of put them all together. I realized after the end of class last time that I let us out 10 minutes early. I didn't mean to do that. Nobody complained, but it's because the clock had not been changed for the daylight savings, and it was off by an hour, but somehow I had it. It messed me up by 10 minutes. I don't know why. Sorry about that. We'll go the distance this time though. So 1:45, right? That's when we're supposed to stop. Okay. Okay. One last trick. This was concatenations. One last trick, which is easy to do on grammars: unions. If somehow the language you're talking about is a union. So for example, let's just so that we don't have to redo a whole bunch of stuff. What if it was this, A to the K, B to the K, union X, where X has an even number of A's. So this is the same sort of two parts, but they'll just be combined together in a different way when we make the grammar. So still the strategy is you make a grammar for each one. This one looks like S1 goes to whatever. This one looks like S2 goes to whatever. Oh no. How to make the union? You should begin. If I don't touch with my fingers, then I think it works okay. Maybe I'll try. I don't know. Begin with. Anyone have a suggestion to get the union? Of course, the union of two sets means or. It's maybe a clue. Yeah?
S1 plus S2.
I don't want to say plus. Sure, I think you mean plus is what I would say if it was a regular expression. There's in a grammar, how do you make or? Yeah. It's the bar, right? I think this is what you meant. The bar. Yeah, and that's all there is to it. So this will make a grammar, a union of two things in your grammar. You use the bar, which represents or. That's how you make a union. This will give you all the things in the first set or the second set. All right. So let's try a couple examples here. I got two examples. I have some for you all to try, although I don't know how far we'll get with those in our remaining 11 minutes. Oh man. Okay, I'm going to try the opposite of rolling my sleeve up. This. Now Now I look really crazy. Make a context-free grammar for this language here. Now, sometimes you have to be a little smart in order to even realize if this thing is a union or a concatenation or whatever. This is one that we did a few minutes ago, but actually I would like to try to think of this as if it were a concatenation. A to the n, B to the m. So you could think of this as just balanced, but there are extra b's, which is fine, but just because we're trying to talk about concatenations and such right now. Another way to consider this is I can think of this as a concatenation, even though it's not obvious. Can I say, actually, first of all, this is not a concatenation of A to the N and then B to the M, all right? Can anyone say what's wrong with that? I mean, it certainly looks like it when it's written there. It is A to the N followed by B to the M. But you might think, can't I just make it grammar for each of those two things? And these are not easy. I would say S1 goes to A S1 or epsilon, and then B S2 goes to B S2 or epsilon. This is wrong. But does anybody see the problem with this? And then you put them together? Yeah.
It's because m has to be greater than n.
Yeah, it's because if you split this up like this, then you forget about this part, which is really important. I mean, that's kind of the whole thing here, right? If you split these apart, you turn them into two completely unrelated sets, then you have no way of making sure that the m is bigger than the n. You lose the ability to handle that. So you cannot split it apart like that. You can't sort of divorce the n from the m because they are related to one another. So don't do that. It is, though, this actually worked pretty well. It is a concatenation like this. Check it out. Ah, was working. A to the n, B to the m, concatenated with, I'll just say, B to the I. Some extra b's. What? This is not what I meant. B to the n is what I meant here. Sorry. The way I'm thinking about this is you have some amount of the b's which actually do balance exactly with the a's, and then you just have some extra b's, all right? That's how I'm trying to think of this. In the original language, sorry, I scrolled it, there are more b's than a's. I'm breaking this up in this somewhat cute way where you can break it up so that we do have, this first part has exactly the same amount, and then there's just some extra b's over here. And each of those I can make a grammar for. You know, the first one is S1 goes to A, S1, B. This one is S2 goes to B, S2, or epsilon. And then we combine them together with the concatenation strategy. So it'll say S goes to S1, S2, S1 goes to A, S1, B. Sorry, I need an or epsilon there. S2 goes to B, S2, or epsilon, right? Yes?
For S2, would it be epsilon or would it be B? Because you can't do 0.
Yeah, this is not supposed to be 0. Thank you for that. Yeah, these should be really extra b's, not allowing for 0 b. So this epsilon should be a b to make sure that we get at least one b in there. Thank you for that. B, B, B. Great. All right. I got one more. Maybe we'll just start off next time with doing some examples for you all, since we got 5 minutes, 6 minutes. I don't mind stopping a few minutes early. How about A to the n, B to the n, n not equal m? This one's a little tricky. Again, it doesn't look like a concatenation or a union, but we can, by some cute idea, we can express this as some kind of concatenation or union. And I'll give you a hint, it's not a concatenation. If you look at this, you may be tempted to, first of all, one temptation would be, can I just say it's a concatenation, A to the n as one thing and B to the n as the other thing? No, because in this case, sorry, it's an M. I'm going crazy here. Sorry about that. This, everybody knew what I meant, right? some amount of A's, some amount of B's, but they're different amounts. Again, you cannot just split apart the A's and the B's because there's a relationship between the N and the M. And if you split them apart, then you lose that relationship. So this I am not going to write as a concatenation. And unfortunately, you can't do a similar trick like this, where part of it is balanced and then there's some extra, because in this case, you don't know which part has the extra. There could be extra A's, but there could also be extra B's, and it's both of them. You don't know which. Anybody have a cute idea here? To write this as a union of two things. Yeah?
A to the N, B to the M, such that N is greater than M, and A to the N, B to the M, such that N is less than M.
Yeah. So what I just said was, the problem here is you don't know which one is bigger. But you can just say this is a union where the one is bigger. It's amazing. Try one more time. A to the N, B to the M. Yeah, if I don't touch where N is greater, union A to the N, B to the M, where M is greater than N, right? Very cute idea. And now each of those two things we can do. Actually, each of those two things is the same as this example that we just did, only one way around or the other, right? This example that we just did is the one where the B number is greater, and the other way around would be the one where the A number is greater. So I'm going to try to write this down. Now I'm going to have so what you have to do is take basically two copies of this and stick them together using a union. So my strategy for writing that is I'm going to say S goes to S1, S2, or T1, T2. And S1, S2 are going to be exactly the same as these ones up here. T1, T2 are going to be the same as these ones, but using extra A's instead of extra B's. So I say, sorry about my handwriting, S1 goes to, for the S's, I'm copying exactly what you see at the top of the screen. B, S2, or B. And now for the T's, I'm going to copy what you see at the top, but use extra A's rather than extra B's. And what that means is that at T1 will be the same, but T2 will change. These B's will be A's instead. So it says T1 goes to A, T1, B, or epsilon. T2 goes to B, T2, or B. Like so. This is basically a union of two different copies of the example that you can see at the top. All right. And I think that'll do for today. We got 2 more minutes, but that's okay. We'll do some more examples of this next time, and you'll have some on the homework to check out.